Aaron, fantastic question. The question before break was, we asked about what chance is on Monday, and then got away from the answer. But believe it or not, you guys just did answer what chance is. So let's recap. With solution number 1, which was put all the white marbles in bowl 1, all the black marbles in bowl 2, there was a 50% chance of living. With solution number 2, there was also a 50% chance of living. With the solution number 3, there was a 72% chance of living. And with solution number 4, there was a 74% chance of living. So we keep using percent chance. So there's an intuitive gut feeling that all of you have for probability, for sure, totally. And you know that that's the way to go if you want to live. You want to do solution 4 if you don't want to die. So the question is, what does the 74% mean as far as the chance is measured as 74%? And Aaron asked a subsequent question that I want to get into later. But let's answer that question first. Tell me your name. Brittany, go.
Hold it out 100 times, 74 times you go.
That's an awesome way of thinking about it. If you were to replicate this experiment, say 100 times, you could expect on average to live 74 out of every 100 times. And if you put the word on average in there, you take care of any silliness. Because it's possible, isn't it? It's possible to run this experiment 100 times, and maybe you only live 70% of the time in that first 100, right? Or maybe even 0. It's unlikely but possible that you could do 100 pulls and never live under this scenario. It's just unlikely to happen, correct? But on average, over time, for every 100 pulls, you're going to live 74 of those 100. On average, over time. So if you look at, if you were to line up, say, an infinite number of prisoners, I know this is ridiculous because you don't have this. Well, in America, we're getting there. You have an infinite number of prisoners, and you give each of them this scenario and make them each do it. And you keep track of live, die, live, die, live, die. Let that go out for a long period of time. What this tells you is you're going to have 74% of people in that line that lived, and the other 26 died. It doesn't mean that out of every 174 lived. It means on average. That's what you were getting at, Brittany.
Yeah.
Whitney or Brittany?
Yeah, that's what I was going to Brittany.
Brittany.
I was going to say, doesn't it reduce the variable mess-ups the more times?
Yes, because you get less of the fluctuations that happen in a small observation. Yeah, you get way less fluctuation, assuming the process isn't changing, which this is not. The marbles are staying in their bowls. So there's a 74%, which means 74% of the outcomes are live, whereas the other ones were at 72 and 50 and 50. Does that kind of make sense? It's not a promise, it's a probability. So this is Aaron's awesome subsequent question, which was, do you remove the chance when you analyze it mathematically like this? No, you haven't removed it, you've just identified it. You know that when you're reaching out and grabbing a marble, you might still die. You just know the chance of that now. It's no longer a question mark, it's no longer like, oh. It's not 50-50 necessarily. It's 74, which means you're more likely to live than die. It begs an interesting question, which is called the Bayesian question. The Bayesian question is, yes, but you get one shot. You either live or you die. It's like the Monty Hall question that we'll look at later on in this course. What should you do? You get one game. Well, to decide what to do, you want to maximize your chance of winning, or in this case, living. So you analyze lots and lots of trials to pick the one solution that maximizes that chance. So, Aaron, does that make sense? That answer your question? It's a fantastic one. You haven't removed the chance, you've just properly measured it. Because there's still a chance. There's still a chance. You either live or you die. But now you know how to maximize the one and minimize the other. As much as you can, anyway. Is that fair? You guys buy that? Fantastic. Thank you for that question, sir. It was wonderful. Wonderful. Other questions before we move on? The rest of this might feel a little dry by comparison to this. Michelle, go ahead. No, go ahead. What was your question? You sure? You positive? Okay. Okay. All right. So what I want to do next, before we get into the rest of the course, I do want to fuse constantly, any chance I get, I want to fuse the idea of this averaging and this probability with whatever topic we're in. Starting on Monday, we're going to take you guys outside. Hopefully it's a day just like today where the sun's out and all the snow bombs have finished dropping. Anybody get hit with one walking here?
Yes.
Yeah, pretty fun, huh? It's like, hey, welcome to Bend in April. We're going to be checking grades of stairs, so it involves some measurement and some little bit of trigonometry and things like that. Little tiny bit we'll learn as we go. The next idea, I want to teach you guys about similar triangles, which is actually just about as far away from probability as you can get, but it's still a useful life math skill. But I want to bring, whenever I can, this back. Now, I know this probably felt like a completely different kind of math problem you've ever done before. Maybe some of you have. Has anybody ever taken a prop stat course before in high school? A couple of you. Oh, no. Only very few of you. Good. So that probably feels like a completely alien kind of math problem, at least in some parts. Once you got going, it's like, oh, this totally makes sense, right? Yeah, of course it does. That doesn't mean we can toss algebra completely. We still need algebra. For example, Ryan, the Bridge on the River Kwai example you brought up, which I then followed with the De Niro casino example, the actuaries have to know what to set certain payouts at to guarantee revenue keeps coming in from games versus going out. I'll give you an example of that. You know the game, it's that Keno. It's pretty popular around here in all the bars, little digital Keno, 80 numbers or something, and you pick a certain number of them and you try to match certain ones. There's a similar game in New York State called Pick 4 or Pick 5 or Pick 3 or something like that. And there's certain payouts based on the results of what you get. So if you match like 4 numbers, you win $10. If you match 3 numbers, you win like 5. It's like Powerball in that respect-ish. So there's certain payouts that guarantee income for the lottery association. You know, they pay out money that sounds great, but it's still overall more people lose than win. So they bring money into the lottery, which then gets dispersed out via all kinds of state programs. Yeah, please.
There's also the percentage of the people who have the actual lottery machines who get the profit as well as the lottery.
That's true.
But it's a smaller amount.
It's small enough to control for. If you know how often hits are going to happen, you can then control those payouts too. And that's part of knowing how often the hits are going to happen. Well, what happened in New York about 4 or 5 years ago, in one particular game, they doubled all the payouts for this one particular game. They said, you know, it used to be if you hit 4 numbers, you got paid $10. Now you get paid 20. If you hit 3 numbers, you got paid 5. Now you get paid 10. Well, what they didn't calculate by doing that was that actually shifted the odds in the favor of the player. You still won and lost at the same rate, but now the average winning was no longer negative. It was positive. Which means they want the average winnings to be negative, because negative for you is positive for them. But it shifted over. They didn't do the math on it. These 2 kids that were taking a class similar to yours figured that out. They went to the casino. It only happened on 4 days. I think it was the month of March. Wednesday from like 12 to 3, the month of March. They borrowed a bunch of money. They're college students. They borrowed a bunch of money. They said, I got a guaranteed return on this investment. And their friends were like, what do you mean? I'm like, I guarantee I got 120% return or 20% return on your investment. They're like, you're telling me if I give you $1, you're going to come back and give me $1.20 at the end of 4 weeks. And I was like, yep, I guarantee it. If you give me 100, if you give me $100, I'll give you 120. If you give me 1,000, I'll give you 1,200, and so forth and so on and so forth. And all they did was they walked in and they started buying automatic tickets. They walked up and slapped down $5 and said, give me 5, give me 5 more, give me 5 more. As quick as they could, they bought, because they knew the payout was guaranteed on average over time. They lost at the same rate they lost before. But when they won twice as much, and that tipped the scale over. Each of them made about $150,000 in 4 days.
What?
Dang. In 12 hours of work. So that's the importance of being able, they used a little teeny tiny bit of algebra and a little teeny tiny bit of this. It wasn't much math at all. When I saw that, I'm like, why was I living here then? But that's the thing. That's the thing. You can fuse the 2 worlds of algebra and statistics and probability and have these beautiful results. Now that's a very, very, it's a fun example, but it doesn't happen very often. What happens more often is deciding on what kind of healthcare plan you should sign up for. Should you sign up for a high deductible? Should you sign up for the Cadillac plan? What kind of car insurance should you buy? Should you get that collision coverage? Should you? Statistically, should you get it? It costs more. Is it worth it? I don't know. Do you have a 16-year-old? Maybe. So the idea is, can you fuse these 2 worlds of algebra and statistics to get some meaningful results? So that's what I want to fuse this with today. I want to start what's called Equation Boot Camp. Oh, just relax. Equation Boot Camp. This is going to shake, and it's all, today is just linear equations. It's all I want to do today are linear equations. All I want to do today. Because these are the equations those kids solved. Pure linear equations.